I'm Hampton Terry, Norfolk State University student. I'm a junior optical engineering major. I'm here at Rose-Hulman with...
And I'm Joe Breaker. I'm a Rose-Hulman junior optical engineering major. And we're going to talk to you today about PN junctions.
Let's start off by talking about conductivity. All materials possess a certain level of conductivity. Conductivity is dependent on the material's band gap, which is the distance between the valence and the conduction bands. The electrons are stored in the valence band and travel to the conduction band. The greater distance between the two, the more energy it requires for electrons to cross the gap. Conductors have the shortest distance, and even some overlap, while insulators have the largest, and semiconductors would lie right in the middle. Semiconductors tend to be silicon, germanium, or gallium arsenide. Insulators are plastic or rubber, and conductors can be metal. PN junctions are typically made from silicon, germanium, or gallium arsenide. They can be called either a diode or a semiconductor diode, and they're commonly used in solar cells, photodiodes, LEDs, and even laser diodes. So how is a PN junction made? We take two semiconductors, a p-type and an n-type, and combine the two. The p-type is an electron acceptor since it has electron deficiencies, or holes. The n-type is an electron donor. In simple terms, the holes are positive, designated by the white circles, and the electrons are negative, designated by the black bars. There is a region near the junction where these electrons and holes combine, a depletion region. As shown by the yellow border, the combined holes and electrons, the black circles, drift towards one another and combine in the region. This process will last until an equilibrium has been reached. This is often referred to as thermal equilibrium. This is a current voltage graph of our PN junction. There are two states the junction can be in, forward and reverse. Also notice the breakdown region. This sets the limit to the amount of voltage applied in reverse bias. Leakage currents are generated from electron-hole pairs generated by temperature.
Breakdown occurs when a sufficiently high reverse bias voltage is applied. Once reached, the diode will conduct current in the reverse direction. This means that holes and electrons will start combining again. When this happens, the temperature will also increase greatly. The rising temperature contributes to the speedup of the combination process, causing the current produced to increase exponentially. This process will continue until the components in the diode melt and break. Typically, the voltage limit is about 10 volts. Reverse bias. When the voltage is applied in the shown direction of the figure, the positive charge attracts the electrons while pushing away the holes. This keeps both the electrons and the holes from the junction and prevents conduction. This is also known as when the diode is turned off. Forward bias. When the voltage is applied in the shown direction of the figure, the positive charge from our power source pushes the holes and attracts the electrons. This further increases the combination of electron-hole pairs at the depletion region. When we apply a strong enough voltage, our diode turns on and starts generating current in the forward direction. For silicon diodes, the activation voltage is about 0.6 to 0.7 volts. The ideal diode equation expresses a diode's current as a function of its voltage. The equation is I of D equals I sub 0 parentheses E to the power of QV over KT minus 1. I sub 0 is the reverse saturation current, which is about 10 to the negative 9 to 10 to the negative 15 amps. I of D is a net diode current under forward bias. Q is the charge of one electron, which is 1.602 times 10 to the negative 19 coulombs. V is our diode voltage. K is Boltzmann's constant, which is 1.381 times 10 to the negative 23rd joules per Kelvin. And T is our temperature in degrees Kelvin. Our ideal diode equation is derived from its original equation, I of D is equal to I sub D minus I sub 0. I sub D is our diffusion current, which is equal to I sub 0 times e to the power QV over KT. Using this, we will prove the minimum activation voltage for a silicon diode at 300 degrees Kelvin. So here's our ideal diode equation. Remember, you have I of D is equal to I sub 0 times e to the QVD over KT minus 1. This is derived from our original equation, I of D is equal to I sub D minus I sub 0, where I sub D is equal to I sub 0 times e to the QVD over KT. So we plug this in for our I sub D, and we get I sub 0 times e to the QVD over KT minus I sub 0. We simplify this equation to get our original ideal diode equation. Over here is what each variable means. K, our Boltzmann constant, which is 1.31 times 10 to the negative 23rd joules per Kelvin. T is our temperature, 300 degrees Kelvin, which is room temperature. Q is our fundamental charge of an electron, which is 1.602 times 10 to the negative 19 coulombs. I sub 0 is our reverse saturation current, which we're going to assume is at 10 to the negative 12 amps. And VD is our diode voltage, and this is going to be our variable that we're going to find out. So when we come back over here, we know that Q over KT will be constant because those are all constant values. So we have the charge of an electron divided by the Boltzmann's constant times the room temperature, which gives us 40. So we're going to designate first our diode voltage to be 0.5 volts. So we're going to do I of D is equal to 10 to the negative 12, which is our reverse saturation current, times e to the 40, which is our constant Q over KT, times 0.5, which is our diode voltage, minus 1. This gives us a current running through the diode at 0.485 milliamps. Pretty small. So this time we're going to do 0.6 volts as our diode voltage. So we're going to run through the same equation again, and this time we get 26.5 milliamps, much larger than the first time. This time we'll do 0.7 volts, run through it again, and we get 1.45 amps, even higher. So as you can see, between 0.6 and 0.7 volts, this is where our diode starts producing our actual current that we want, and that's when it actually turns on, and that's how we do the ideal diode equation. So now you know how to do PN junctions. So when you go talk to your teacher now, you won't be entirely clueless about the class, but trust us, it's a hard class.